You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Scott Solomon. Dr. Scott Solomon is a biologist, professor and science communicator at Rice University, where he teaches ecology and evolutionary biology. He's also a research associate at the Smithsonian National Museum of Natural History. His work explores how life adapts, from microbes to humans, including how spaceflight may shape our future evolution. He is the author of Becoming Martian and Future Humans, and has created widely viewed courses, documentaries, and podcasts on science and evolution.
Dr. Scott Solomon, welcome to the program.
Thanks so much. Excited to be here.
Now, Doctor, you're an evolutionary biologist and with a specific interest in ants, and I will get to that later. But you've recently written a book, actually two books, Becoming Martian and Future Humans. And the idea is, all right, humans adapting to living and working in space long term. What are the current problems that we see just with the International Space Station and Mir and all that? What are the current problems that we see that with astronauts coming back to Earth, even after just being up there for months?
Yeah, I mean, astronauts that are in space on ISS or any space station, they're experiencing weightlessness, right? And so muscles and bones become weaker. Bones lose density at a rate of about 1.5% to 2% per month. Muscles, can pretty quickly atrophy, especially the muscles that are used to kind of hold the body up against gravity. If you watch the videos of the astronauts coming back, right, like they always need help to get out of the spacecraft. Sorry, turn my phone off here so we don't get interrupted. So astronauts always need help when they come out of spacecraft, and that's because basically they've been deconditioned. I mean, it's equivalent to basically being on bed rest for a prolonged period of time. And actually, that's one of the ways that researchers study the effects of weightlessness for prolonged periods. In addition to studying astronauts. So, a rule of thumb is that it takes about as long to recover from being in space as you were in space. So if you're there for 6 months, it's roughly a 6-month recovery from coming back.
It strikes me from evolutionary history from that point of view. You're taking a human outside of what it evolved, or he or she evolved to. We are specific to our niche, our environment, and space is not that. And just like when, some sort of a change in climate or whatever can kill a species, space can kill us instantly. And it's the most harsh thing. So we're basically transporting Earth's biosphere whenever we go into space.
Yeah.
Are there ways that you can see, though, that we can sort of adjust and start, let's make a GMO human, genetically modify a human to be better suited for space? And would that be ethical if we did it?
Yeah, so we could probably spend a full hour just unpacking that question, honestly. So let me try to break it down a little bit. You make a really good point that we have throughout our evolutionary history, not just our species, but our entire lineage. As much as the environment has changed, as much as the Earth has changed, one thing that has never changed is the strength of gravity. So that is one thing that has remained constant throughout our history and the history of life as far as we know it. 4.5 billion years of evolution on Earth. Taking humans or any organism out of that environment is a change unlike anything we have ever experienced in those 4.5 billion years of history. So it is a profound change. You asked about, what are some of the ways that we can adjust or adapt? And I always like to point out, as an evolutionary biologist, that word adapt, like we use that word differently in the context of talking about evolution than we often use it in everyday speech. So sometimes we talk about astronauts that when they go up there, they adapt to the conditions. That's a different kind of adaptation from what we as evolutionary biologists talk about a species adapting to its environment, right? So an individual can't adapt in an evolutionary sense. We can acclimate or adjust our bodies. So similar to how, like, if you go up to a high altitude place, when you first get up there, if you're from sea level like I am, I live in Houston. If I ever go up to the mountains in Colorado or anywhere else, it takes me at least a week to start to feel like I'm not completely out of breath, right? And that's my body acclimating, adjusting to the thinner air. So astronauts can acclimate or adjust to the conditions of space to a certain extent, right? Astronauts, when they first get to space, are often dizzy, motion sick even. That's a common thing that astronauts experience. The fluids have rearranged themselves in their bodies. Fluids that were down in their legs are up in their heads. And, it takes a little while for the body to kind of compensate for that. So there's a lot of things that the body can do to adjust to being in space. But there's also limits to that, and we can get into more of that if you want. But yeah, you also asked, could we, sort of manipulate our bodies in ways to kind of help to make it easier to be in space, right? Could, like, future people living, say, on the moon or Mars or in a space station, if they're there for a long time, could we kind of help them out by maybe using, gene editing techniques like CRISPR to kind of jumpstart the adaptation process? And some people are actively working on that. So in my book, I describe visiting the lab of a researcher named Chris Mason at Weill Cornell Medicine, who is actively working on trying to see if you can basically get genes from tardigrades, which are kind of famously good at being in extreme conditions, including space. If we can, take some of their genes, put them in human cells, and give humans some of those abilities. So early stages still of doing that, but people are actively working on it. Now, you also asked me about the ethics, but I feel like I've been talking for a long time, so I don't want to, okay, all right. So I'll just say a little bit about. I think it's actually really important that you asked about the ethics, because I think that's a very, very important part of the conversation. So, it's like the quote from Jurassic Park, right? Yes, the scientists can, but did they stop to think of whether they should? So, I talked with actually Chris Mason about this quite a bit when I visited him, and I've talked with others. And I think, researchers that are thinking about this are certainly aware of those ethical concerns and take them seriously. Everybody that I've spoken with certainly does. So, yes, those are very important questions. I think the first step is to figure out, like, what are the changes that might be made? And do we understand the safety of those changes? Do we understand any possible unintended consequences of making those changes? If those changes could be done safely, if they could be done without, unintended consequences, and if there's a strong enough motivation to do it, right? Why are we trying to do this in the first place? If it's something that is truly necessary to alleviate human suffering, then I think, an argument can be made that it might be an ethical thing to do. But that's a lot of ifs. So I think it's an important conversation to include as we're talking about our future in space.
Of course, and the ethics of, putting someone in space for long term, which we'll get into that with generational ships, because there are a lot of ethical questions there. But that would make for a wonderful horror movie, however. The idea of, like The Fly, but it's a human that's merged with a tardigrade.
Oh, yeah, the tardigrade.
That would be a good one. But let me ask you this. Now, time is a factor here. So if you go up to space, you're on the space shuttle, you're up there for a week, back when we had the space shuttle operating. You're up there for a week, you come back, not so bad. You're sitting up there for 4 months on the ISS, different story. And you end up, you're just not used to gravity, as you mentioned.
Yeah.
So what about longer time frames? Mm-hmm. For example, send somebody to Mars, astronauts to Mars. They go and spend whatever amount of time there and then come back, and they've been gone over a year, and they've been in space and a low, gravity environment like Mars, which is 2/3, something like that. What does that look like when they get back? I mean, how do you get them rehabilitated after that long in space?
Yeah, I mean, prolonged space definitely has a significant effect, right? So, the NASA twin study was kind of, our first detailed glimpse at what the all of the sort of changes, or at least many of the changes to the human body during a long duration flight that was about a year in space that Scott Kelly spent on the ISS. And there were pretty profound changes. I mean, some things that were kind of expected in terms of muscle atrophy and bone density loss, but weird things like his telomeres and his chromosomes actually got longer. Normally, your telomeres get shorter with every cell division, and his got longer. And that was like a really unexpected result that has since been replicated even in short duration space flights. So there's something going on about the space environment that causes telomeres to get longer. So happy to talk more about that if you'd like, but just sort of generally speaking, there are things that happen that are sort of like not issues when you're going up for a short like a suborbital hop. If you go up and come right back down and you're up in space for a few minutes, like you're not going to experience a lot of the issues that we were talking about with muscle and bone and all of that. One of the other issues that comes up in long duration space flight is vision deterioration. So there's this condition now, which has an acronym. It's called SANS, SANS, Space Associated Neuroocular Syndrome. And basically, astronauts have in many occasions noted that their vision got worse during a long-term space flight, and that was true for Scott Kelly during the year that he spent as part of the NASA twin study. It's thought that is due to those fluid shifts I was talking about earlier. So with more fluid in the upper body, it seems that there's increased pressure on the eye, and that appears to be causing this thin layer behind the retina called the choroid to essentially buckle and fold. And that seems to be what's causing this vision loss. And so, of course, that's like a really serious concern. I mean, if people are going, as you said, on even longer missions, for example, to Mars, the last thing we want is for them to come back with, major problems with their vision. So in terms of going like to Mars, right, we know that with current propulsion technology, it takes between 6 to 9 months to get from Earth to Mars. And of course, you can only do that during certain windows when the planets are relatively close to one another. That happens about every 2 years. And then because by the time you get there, the planets have moved farther apart, you have to wait for them to come back around again in order to go back from Mars to Earth. So you're looking at a round trip of at least 2.5 years. So that's a long time to be away from Earth. And as you said, you would be in a lower gravity environment the whole time. On the way there, you'd be in a zero G, in a weightless environment. On Mars has 3/8 of the gravity of Earth. So that's about a third. We don't really know what that does. That's an interesting thing to point out, is that obviously we've learned a lot about what happens to the body in a zero G environment, but we don't know what happens between kind of 0 and 1, right? There's been only 12 people that have ever experienced partial gravity for any extended amount of time. And those were the 12 Apollo astronauts that walked on the moon. They were in a 1/6 G environment, but the longest that they spent there was about 3 days. We have no idea. I mean, we can guess, we can speculate, we can kind of extend the line if you're picturing a graph and kind of what's happening to the body over time, right? But it's just speculation. So remains to be seen what will happen to a human body for 2 years or so in the partial gravity of Mars.
Now, I have two questions, and I'll ask them separately. The first one is, you piqued my interest with telomeres because those are implicated in life extension type science. And if you can extend those, maybe you have a better chance of extending the lifespan of the organism. So do you expect that people living in space might actually live longer as a result?
Yeah, I mean, when this first was reported, I think some people were like, "Oh my God, we found the fountain of youth! It's space, like go to space, you'll live forever." And of course, probably not as good as that. There's many ways in which being in space actually resembles accelerated aging. So, I mean, that actually made the telomere result perhaps even more surprising, right? You would almost imagine like that they would get shorter faster. Yeah, I describe telomeres as almost being like an hourglass, right? So we think that basically so essentially telomeres are the caps at the ends of chromosomes, and they serve kind of a protective role. So as telomeres get shorter, you can have more damage to the DNA in your chromosomes. And so we think that that is associated with aging. So when your telomeres get really short, that's when some of the kind of ways in which the body breaks down with old age start to happen. So getting longer, as you said, is like, looks like reversing aging. But here's where I'm going to throw a big bucket of cold water on that idea because, well, two things I'll say. One is that when you come back to Earth, the telomeres go back to how they were. So in order for that to if it were true that telomeres getting longer was indeed sort of like reversing or slowing the aging process, you'd have to stay in space. You couldn't come back. But even that is unlikely to really be as good as it sounds, because one of the situations where we see telomeres not getting shorter is with cancer cells. So cancer cells are sort of like these cells that are essentially kind of immortal or rapidly, taking over because they're not aging in the same way, or at least that's part of what's happening. So actually, I'm not saying that these are cancer cells, but it's sort of like stopping telomeres from getting shorter is a little bit concerning because it reminds us a bit of what happens in the cancer process.
Yeah, that's actually been talked about for decades now. And I remember hearing in the 90s, the people that were looking into anti-aging, they're like, well, if you start extending telomeres, what's that do for cancer? It's almost seems like it would favor it.
Yep.
Now, my second question is, all right, we can spin spacecraft around and create a sort of artificial gravity, but it isn't. Do you think there's going to be a difference there, other than weird effects like if you're in that sort of centrifugal or centripetal force, you turn your head. It's not like turning your head on a planet. You'll get disoriented and you'll have to adapt to that. But fundamentally, do you think that can be a viable proxy for gravity insofar as we know?
Yeah, I mean, I think it's a possibility. I think if we could actually create spacecraft that were able to spin in a way that created a force that was similar enough to gravity, that might be a way of minimizing the effects that people experience on the way to Mars, or if we're talking about going farther, or spending longer amounts of time. We don't know because nobody's ever done it, right? So as you say, it's not maybe exactly the same as gravity, but if it could minimize muscle atrophy, bone density loss, vision changes due to fluid shifts, certainly those would all be great things to avoid. And those are serious concerns. We haven't even talked yet about one of the other big issues, which is like human reproduction. So the whole idea of, could we actually live in space or on Mars or anywhere else, kind of assumes that we can reproduce. And the effects of gravity on all of the stages in reproduction are largely unknown. So another context in which it would be really wonderful if we could have artificial gravity would be for, pregnancy, childbirth, and possibly for child development as well.
And there we go headlong into the generational starships, because there you're going to have some kind of reproduction as long as people have finite lifetimes.
Yeah.
And the sad truth is you can't live forever, because eventually the meteorite hits you or something like that. And I've seen estimates that statistically, 50% of the population can only make it about 10,000 years. They can't live forever before an accident happens and something, takes them out. But in the case of the generational starships, this is where you have people that are born, live, and die on this, generational ship, whatever form that might take, a hollowed out asteroid or whatever, giant city inside of an asteroid. I don't think Homo sapiens, as we have evolved here, could do it. I think there's too many daunting tasks, and reproduction is one of the chief ones. Even if you had artificial gravity going on with a spinning asteroid or whatever, you're still, you're just not where you are supposed to be ultimately, right? What problems do you see with the idea of generational ships?
Yeah, I mean, I think, it's a really interesting thing to think about. So a lot of the issues that you would face are issues that I think would be true of us going anywhere really beyond Earth, anywhere where we have such a radically different environment. So different gravitational field is one of the challenges. So, even if we suppose that we could create artificial gravity and sort of eliminate that problem, the next question I would have is, what about radiation exposures? Are we able to kind of block galactic cosmic rays from damaging DNA? Maybe if that's possible to do, then that would be good, because we know that could be really harmful. One of the other issues that I think is an important one to consider is that, in addition to always having been in a 1G environment throughout our evolutionary history, we've also always had other organisms around us. We've lived in an ecosystem for our entire evolutionary history. So, we know that the microbes that make up our microbiome are actually essential for our health and well-being. And we know that astronauts take microbes with them when they go to space. So there have been interesting studies of how the human microbiome changes when astronauts go to the International Space Station. So, any astronauts that were to be leaving Earth and embarking on a generation ship, they would be taking some microbes with them, but they'd only have whatever they bring with them. So throughout our evolutionary history, we've had exposure not only to the microbes in and on our bodies, but also all of this rich diversity of microorganisms that inhabit the Earth. And, sometimes we interact with them, sometimes we don't. But one thing that's really important to recognize is that as a child is born and grows and interacts with those microbes, their immune system is kind of trained on how to, fight off anything that could cause an infectious disease, right? And so, our bodies are pretty good at doing that generally. And so most of those organisms don't make us sick. But if a child were to be born into a generation ship and only ever exposed to whatever small fraction of microbes were brought along on that journey, if they were to ever return to Earth, that actually could make them very sick, because then they're going to be exposed to a huge diversity of microorganisms that they had never encountered themselves. And if we're talking about, multiple generations in the future, maybe their parents, grandparents, great grandparents, et cetera, hadn't been exposed to them. Basically, the immune system could potentially begin to kind of atrophy, or at least become very specialized on only certain sets of microbes. So I think thinking about the ecosystem of a generation ship is actually a really important thing. And that includes all of the microbial life.
I would add another dimension to that popped in my head. The plants, they in their soil, they have their own microbiome, and sometimes that's symbiotic, like with beans, you know, and things like that. You lose one of those microbes in that ship, it's gone.
Yeah,
unless you got some genetic way to resequence it and get it going. But are there vital components, microbial components to the human, gut bacteria, basically? That we can't afford to lose if we're on a generational ship?
Yeah, that's a really good question. And we are such at an early stage right now in understanding the human microbiome that we don't actually know the answer to that question, which is kind of remarkable. I mean, it's only been a few decades that we've really had a full appreciation for just how important the microbiome is, and started to really kind of characterize and describe it. And we're still now at the point where we're even kind of like identifying what the different components are. We are only beginning to figure out, like, what do all these things do? Like, are some of them essential? We think that some of them are. We know of a few examples. We also think that there are some that can play important roles in some circumstances, or might just be sort of like, not harmful. And then, of course, there's other things that we know are potentially dangerous. So, I mean, that's a really basic, important question that we still don't have the answer to. That's part of why I feel like we're not quite ready to embark on this. And it's not just because we don't have the technology to make a generation ship or to build a city on Mars. It's because there are fundamental questions about how we would survive that we don't yet have answers to.
Yeah, and there, within the realm of science fiction, bordering on science fact, there are ideas like, for example, cryogenic preservation, freezing someone and then thawing them out, and they're getting a little bit better at that with vitrification and things like that, as opposed to, it used to be just it destroyed this tissue, when you froze a person. Now less so, but those sort of suspended animation type ideas always get cut short by one thing: cumulative radiation exposure over time, because of the radioactive isotopes in your own body. It will eventually give you a fatal dose if you're just sitting there not repairing, for long periods of time and things like that. Do you think that's a viable alternative to this, of instead of sending living, breathing humans, sending frozen humans out there?
Yeah, that's a really interesting idea. Either frozen humans, or maybe we don't even need whole organisms. Maybe what we need are just frozen gametes, just frozen sperm and cells, or even just embryos. Maybe we need to literally seed life on another planet. Of course, that begs the question, who's going to raise them, right? We all know kids need enough help getting raised as it is. Imagine, sort of like, I don't know, Lord of the Flies on Mars. Hey, somebody should write that story.
Raised by an artificial intelligence on the generational ship. I think I'll pass on that one. I think I don't know that's going to lead to particularly well-adjusted humans wherever their destination is. Now on Mars, all right, or the moon for that matter. Let's actually take the moon, because Artemis, the loop around, is coming up. Very exciting, and we're back to the moon, and all right, what do you anticipate just on that short of a journey, those astronauts that are going to loop around the moon and come back on Artemis 2? What are they going to go through? Will we do the same thing that we did with the Apollo astronauts when we actually land and isolate them, which didn't really work, because one of the astronauts actually ironically saw ants coming in and out of the isolation trailer. But what's that going to look like for those astronauts on that journey when they get back?
Yeah, ants are always the weak link in everybody's plans. I've had my plans thwarted by ants so many times. But yeah, so let's talk about Artemis. And what they're going to experience. So, the first thing they're going to experience is what anybody leaving Earth and going to space experiences, which is the high G forces of the launch. This is something that astronauts are trained for. They're well prepared for. 3 of the 4 crew members on the Artemis 2 mission have been to space before, so they know what to expect from that. That's a relatively short duration thing, just a few minutes. But then they will experience weightlessness as they make an orbit around the Earth, and they're going to be doing that as they are checking out their systems and making sure everything is functioning properly. Then once they've got everything ready to go and it's time to make their way to the moon, they're going to turn the engines on once again and have another burn as they go in an orbit or in a trajectory that'll take them towards the moon. So they're going to be experiencing higher G forces again for that. One thing that is interesting that they're going to experience that no humans have experienced since the Apollo era is that they are going to be passing through the Van Allen radiation belts. So this is an area that is basically surrounding our planet in kind of the shape is sort of like, I don't know, if you imagine a rubber band that was sort of stretched out to the sides, right? So you've got kind of these 2 lobes on the side with Earth in the middle. And it's formed by Earth's magnetic field. So the iron core deep inside the Earth that is molten and moving around is creating this magnetic field. And one of the things that does is it traps radiation in these bands known as the Van Allen radiation belts. There's an inner belt, an outer belt. And this is a good thing for us on the surface of Earth, because by trapping radiation, it is reducing the amount of radiation from both the sun and from galactic cosmic rays that reach the Earth's surface. This is part of what makes Earth habitable. All of the astronauts that have been to space in the recent past, since Apollo, basically, are basically still close enough to the Earth that they are inside of that magnetic field. So we haven't actually had anybody pass all the way through all of those Van Allen radiation belts since 1972. Now, luckily, they are going to be passing through them going at a very high speed, and so they won't linger there. You don't want to be hanging out in the Van Allen radiation belts because, again, there's trapped radiation there. So that's not a place that you would want to spend much time. So they'll only pass through those fairly quickly. And then once they get past them, now they are in, essentially in the deep space environment. And they will still be in a high radiation area because being outside of the magnetic field, it's not that there's trapped radiation, but there is all of the radiation of deep space. So, again, solar radiation as well as galactic cosmic rays. So they will be in that environment up until the point when they pass back through the Van Allen belts on their return. But of course, the thing that everybody's excited about here is that they are going to go and orbit around the moon. And one of the things that I think is so cool about this is that they are going to get to two things, really. They're going to get to view the far side of the moon. And I think it depends on exactly when the launch ends up happening, right? Which day it goes as to exactly how illuminated that part of the moon is going to be. But there are parts of that side of the moon that no human eyes have ever seen because they weren't illuminated during the Apollo missions that went around the moon. So that's just such a cool thing that, they have the possibility of seeing with their eyes. And of course, they'll take pictures, parts of the moon that we've never seen. So that's super cool. The other thing that's super cool that they're going to get to hopefully do is take a path that will basically go so far past the moon that they will actually be farther from the Earth than any human ever has. So I think the current record is Apollo 13 that also orbited the moon, but the trajectory that they're planning to take will take them even farther than Apollo 13. So that's pretty cool that they will be the people that will be farthest from Earth ever. What a cool fact. They're going to be in a weightless environment for all of that time. So in that sense, it'll be largely like what astronauts on the ISS or the shuttle or any other recent experience has been. But they'll be looking at Earth from pretty far away. So we haven't yet talked about kind of the psychological aspects of being in space, which are pretty interesting. And seeing Earth from that distance, I think, just has to have a profound effect on you just emotionally, psychologically, right? So yeah, that's gonna be pretty cool.
I think that happens to anybody that goes to space, even low Earth orbit. Look at William Shatner's reaction when he just went up there on Blue Origin.
Yeah. Oh, so. Absolutely. Yeah. No, and there's a lot of work that's been done, kind of trying to describe that, right? The overview effect, as Frank White dubbed it, which I got to speak with him as I was researching the book. It was super cool. But yeah, I think, was it Jim Lovell that was the Apollo astronaut who sort of like put up his thumb and blocked out the Earth? So yeah, of course, looking at the Earth from space, I mean, that's the number one reason I would want to go to space, to be honest. But the idea that it's like Earth looks that tiny in your perspective, oh my gosh, that has to be, sort of like next level mind blowing, I would guess.
Or the perspective of Voyager 2 looking back and, seeing the pale blue dot, just everybody that has ever lived was born, lived, and died on that,
exactly,
that little dot. Now, in regards, one thing more about Artemis 2 is that the Apollo missions, and this is sort of an aside, the Apollo missions detected from lunar orbit weird stuff, especially things like one of the astronauts saw a cloud, like a dust cloud. And there are questions, about the lunar terminator where, you're going from day to night, very, very knife edge, that actually there's an electrostatic effect that might be causing the lunar regolith, or at least part of it, some small fraction of it, to levitate. and then it comes back down. And there's questions about, well, what does that do for any kind of a landing where they have to actually spend a whole night there, because the Apollo astronauts didn't do that. But we eventually will have to, and they're weird questions. So I expect weird things to show up from this Artemis mission.
Yeah, that's super cool. I hadn't heard about that, actually.
It's kind of obscure, but it did happen.
Yeah.
Now, radiation over time, we were talking about radiation. Over time, again, back to the generational ship, unless you're blocking it effectively, which if you've got a hollowed out asteroid, you're probably pretty good, pretty well off. But if you're not, that's going to cause mutations.
Yeah.
You're going to have cellular damage, DNA damage and things like that eventually, it's going to mutate, So my question is twofold here. All right, if that mutation is bad, that's basically cancer, or something like that. That's one thing. But if it gets a beneficial mutation out of it, as it does occasionally happen in evolution, that's how it works.
Right.
At what point do the taxonomists say that is no longer a Homo sapiens?
Yeah. This is such an interesting question. So let's break it down a little bit. So you're right that, generally speaking, we think of mutations as being harmful, right? And the way I like to think about it, it's like, look, this is an instruction manual. Our DNA, our genome is an instruction manual that has been constantly tweaked for the last 4.5 billion years. And if you just go in and randomly change something, the chances are very high that you're going to make it worse. Like, you're just not likely to randomly tweak something and make it better. Now, some of the changes actually don't end up having any effect that we can detect. So we call those neutral mutations. So the vast majority of mutations are either harmful or neutral. But you're right that every now and then there is a change that happens to be beneficial in some way, or happens to be beneficial in that particular moment, in that place and time, that environment, et cetera. And those mutations ultimately are what have given all of the variety of life on our planet. So it's the creative force, so to speak, for evolution, right? Like I always remind my students, natural selection can't make anything new. All it can do is sort out what already is there. It's mutation ultimately that is something that can make new, a new form, a new action, a new ability. And so, it's possible. I think you're right that cancer is a very serious concern with long radiation exposures. The more time we spend in space, the more likelihood of cancer we should expect. This is the reason that NASA astronauts essentially have a time limit on how much time they're allowed to have in space, because NASA wants to minimize the chances that any of their astronauts get cancer. And so far, they seem to have done a pretty good job. The data seem to suggest that NASA astronauts that have been to space are not any more likely to contract cancer than the average population. But if we are spending more time in space, if we are going deeper into space, and especially if we're spending more time in deep space, as you said, if we don't have sufficient mechanisms to block that radiation, then we're gonna expect cancer rates to be high. But I think there is a flip side to it, which is that there's always that possibility that a mutation can be beneficial. So one of the things I like to point out is that it's possible that being in deep space could, in a sense, kind of jumpstart the evolutionary process, right? If it is creating more variety for natural selection to sort through. So it's sort of like, if we can live long enough, so if we're not, just being killed by that radiation, then maybe you can be in that sweet spot where you're able to get some variation from mutations, and those variations can sort of lead to adaptation. But you asked a very interesting part of the question too, which is okay, how much mutation would be necessary for us to now categorize those individuals as being a new species? And you could probably start a fist fight at a biology conference by asking a question like that, because biologists scientists like to argue about everything, but biologists particularly like to argue about species definitions. I tell my students when I'm teaching evolutionary biology that it's sort of the dirty little secret of biology that the species is one of our fundamental units, and yet we can't agree on a definition for what it is. So, probably the most common or popular definition that gets used is that species are able to interbreed and make an offspring that can survive and itself reproduce. So this is why like a horse and a donkey are considered the same species, because even though they can mate and make an offspring, that offspring is a mule, and a mule is sterile. It can't reproduce. So that kind of, matches the definition. If the offspring is not able to reproduce, then it's an evolutionary dead end. So that's one answer I could give is like, if we got to the point where people living off world are unable to have kids with people on Earth, then that is, according to that definition known as the biological species concept, that then they would be considered a different species. But that's just one definition, right? There's gosh, we could talk all day about species concepts. Sometimes they're more based on like physical differences, like they look different enough, or noticeable differences in DNA, like if we could quantify that and say, X% difference DNA, but again, we don't even agree on what that percentage is. So yeah, there's no easy way to answer that. In practice, what most biologists do, like me, when I'm, writing research papers about like saying, hey, this is a new species, say of ant, we usually combine some of those. We'll say, okay, it's physically different and it has this kind of noticeable DNA difference, and maybe it also has a different role in its environment. And if all of those are satisfied, we can be pretty sure that it's a different species.
Now, the psychology of living in space is my next question. To get directly into that, you put a person inside of a sealed spacecraft, a small, generally small environment, and they're stuck there for however long. What does that do to a person psychologically? And I guess the closest thing that you could maybe compare it to would be, submariners, stuck on a nuclear submarine for 6 months. What does that do to the human psychology of the astronauts?
Yeah, there have been a bunch of studies of this, and you're right that nuclear submarine missions are maybe one of the best comparisons that we have. Another one is researchers at polar stations, like in Antarctica. Basically being in an extreme environment, you can't just step outside and go for a walk, and you're stuck with whoever is there with you in a somewhat confined space, right? And so, yeah, I mean, a lot of what it does is it can be extremely stressful, right? And we know that who you choose to go makes a difference. So there's a lot of kind of screening people to, sort of like send people that are the least likely to have issues. But even with that, you still end up having people that have, a variety of different issues during these missions. Being able to kind of have access to mental health care professionals, I think, is an important, component to it. Crew dynamics turns out to be really important, right? So, a lot of what happens in the context of space travel, right, is that the crews that are going to be in space for a while, they spend a lot of time working together in advance, a lot of kind of team building, and that seems to be pretty important, right? Because you get to space and you're in this stressful environment, and you kind of know how to work well together. One of the questions I have is what's going to happen when you've got large numbers of individuals who, aren't highly trained astronauts. If we're talking about kind of everyday people, maybe you can do some screening, maybe you can do some teamwork ahead of time, but if not, the kind of like consequences of having any sort of a mental health crisis in that situation, it could be quite high. And so I think we have to take these questions seriously. Like the psychology of deep space travel is something I think probably doesn't get enough attention.
No, it doesn't. And, it's also high stakes because you can't really, if you've got somebody that's having problems, or go further, a raving lunatic shows up, in space. they're out there, they're stuck there, and anybody else is stuck with them. So I mean, one can run through all kinds of scenarios. I want to change gears though and talk about ants for a bit, because ants are fascinating in that they just have a different way of communicating and a way of operating than humans do effectively. And that to me gives clues on what an alien civilization might be like if they're more like ants. So let's have fun. As a researcher of ants, what would you imagine an alien civilization, or a technological ant would look like? What would their civilization look like, and how would it differ from our Homo sapiens civilization?
Yeah, well, I love making this transition because, as you know, I spent many years studying ants. My dissertation research for my PhD was looking at the ecology and evolution of leafcutter ants in the Amazon rainforests and other parts of Central and South America. So I'm absolutely fascinated by ants. And, I think one of the things that's really interesting is that ants remind us of ourselves because they are social, because they live in a colony, which in some species of ants can be really sophisticated. Like the division of labor that leafcutter ants have reminds us a lot of how our societies work, right? There are individual ants that have certain tasks that they perform. This is the gardener ant that is maintaining the fungus garden, which is the food source for all of the ants. There are other ants that are tasked with, trash duty. They're taking out garbage and also dead ants and taking them to another part of the colony to kind of keep them away so that there's not a disease outbreak. And then there's other ants that go out of the colony and go searching for food, and others still that are in charge of kind of colony defense. So, I mean, that's how human societies function, right? But one important difference that I think is noteworthy is that ants don't have a leadership hierarchy. This is the one striking difference between an ant society and a human society, right? Without a leadership hierarchy. What I mean is, like, there's no ant in charge. We sometimes think about the queen, and this is often what I think science fiction sort of gets wrong about ants or anything that is described as ant-like or bee-like or wasp-like. And even children's stories about ants often kind of portray the queen as like a dictator or something like that, or at least a queen in the sense of a monarch. They're not. All they do is lay eggs, and so they're not controlling the ants. They're not telling them where to dig or where to go find food or even who should do that. So one difference that leads to is like there's no concept of like an abuse of power, right? Or like a corruption or something like that. And so I think, I've thought a lot about sort of like what are maybe some practical lessons that we can learn from ants. I think that's one, right? Is like a lot of what happens in human societies when we have issues is because of a breakdown in that leadership hierarchy, right? Somebody's doing something they're not supposed to be doing, often at the top, right? And so I think that's an interesting difference. So if there is, an alien society that is modeled like ants, it would have to be one that doesn't have that leadership hierarchy. There are downsides to it. I think, there's reasons why we keep building whether it's a company or the military or, a university, right? Like we always have this sort of leadership hierarchy. There are benefits to doing it, but there's also downsides. So, yeah. Anyway, I could talk all day about ants.
Well, I have actually a specific question about ants. So, all right, how do they delegate if they have no authority? How do they delegate tasks? This ant is going to go and do this job. How does that happen? Do they somehow collectively do it? And I don't know, do they communicate chemically or what are they doing?
Yeah, it's a little bit of both. So part of it is instinct. So they're not, an individual ant is not particularly intelligent. They have sort of a limited range of tasks that they can do and, ways that they kind of can interact with the world and with each other. But yeah, so it depends on the ant species, but a lot of them, what happens is that their tasks change with age. So when they're first born, they have certain roles, and then as they age, their roles change. So one example of that is like the foragers, the ones that go out of the nest and look for food, are often the older ants. And so that is something that seems to be kind of built into their instinct that like once they reach a certain age, then their role changes. But in other species like the leafcutter ants, that's actually not the case. They're kind of born into their roles, and it's in part based on their size. So there's like the teeny tiny workers never leave the nest. The biggest workers are the soldiers that are really specialized in defending the colony, and they have these big giant jaws that can cut through skin and yeah, they're formidable. I can tell you from experience. And so those are sort of like genetically programmed or not genetically programmed in some cases. We actually don't know a lot still about kind of how an individual ant becomes, a particular caste, as we call them, like a particular, role. But yeah, somehow it's kind of baked into to the way that they're born.
I always found it poetic in a certain way that, ants included in this and, quite a few insects, is that we actually mimicked them with, our rovers have 6 wheels.
Yeah.
And we've thought, 6 legs seems to be better for walking across exoplanets or planets like Mars than, bipedal. We're weird. We're strange over here in primate land. But the insect world just sort of hit, exactly the right formula for their terrain, because they're walking over pebbles and all kinds of things.
Yeah.
And here we we mimic it because it is the best design that evolution came up with.
Well, that's true. Yeah. I mean, it's a remarkable fact that half of all species on Earth that we know about are insects, right? And like you said, so they've hit on a formula that clearly works well. Having 6 legs is a part of that, having a segmented body where you can kind of specialize each part of the body in different ways, different kinds of mouth parts, etc. So clearly being an insect is a successful strategy. So yeah, I wouldn't be shocked if some forms of alien life kind of resemble insects in one way or another.
Wouldn't shock me. And it's interesting because if you look at mass extinctions throughout Earth's history, only one of them was bad on the insects. The rest of them, they just sort of shrug it off for the most part and, move on.
At least some of them. Yeah. Right.
At least some of them. But, you're going to lose something no matter what in a cataclysm like that. But the insects tend to fare better than, not as well as the microbes do, but they tend to fare better. But than the mammals do anyway. And I always found it interesting that as we explore space, we're actually mimicking mimicking nature in some ways, and because of you can't beat millions upon millions of years of evolutionary trial and error.
Exactly. Yeah. I mean, because through evolution, organisms have tried just about every strategy that could exist, right? And so natural selection sort of takes those that work well and makes them more common. So that's kind of what we get. Yeah. So yeah, exactly. But you're right.
It boils down the good stuff for us.
Yeah. Exactly. And I think we should keep doing that. I think we should do it more deliberately. We should look for what are the solutions that other organisms have come up with for living in particular contexts if we're going to be trying to live in space. So, people often ask me, like about, well, what's the connection between ants and space? It seems like there isn't much of one, but actually one of them that I think I would like to put forward is that if we are going to live underground because we need to be basically protecting ourselves from radiation, like you were talking about on an asteroid or even on the surface of the moon or Mars, right? Where we need to be protected under that regolith from radiation exposure. Hey, ants have been doing this for, 120 million years. They have learned how to build a complex structure underground that allows for that kind of complex society. Why not model our habitats after an ant colony? So, I'm available for consultations if anybody wants to explore that idea.
A giant ant farm full of humans. I love it.
Right.
All right, Doctor. Where can everybody get your books and tell us about them?
Oh, yeah. So, okay. Thank you. So, my first book is called Future Humans: Inside the Science of Our Continuing Evolution. And it's really an exploration of the ways in which human evolution is still happening today. Everything from natural selection operating to, make people with certain genetic traits more common, to other forms of evolution like gene flow, the movement of genes between populations is actually a really important part of evolution today, and sexual selection, the ways that mate choice can influence our evolution today, which I argue is more important today than it ever was at any point in our history. So that was my first book. And then at the very end of that book, in the last chapter, I kind of try to look at our long-term future. And that was where I first kind of explored this idea of what would happen to us from an evolutionary perspective if some people left Earth. And that was a book. That book was published in 2016 by Yale University Press. Still available on Amazon and other booksellers. But what I decided to do after that book came out was sort of explore that thread. And so the new book, Becoming Martian: How Living in Space Will Change Our Bodies and Minds, published by MIT Press in February. And it's available also on Amazon, lots of other booksellers as well. And it really explores a lot of what we talked about today. What are the ways in which being off Earth in various environments, including Mars, but not limited to Mars, how does that affect the human body? And how can we apply what we know about evolutionary change to think through what would happen to future generations living out there in space?
All right, we are out of time. Thank you, Doctor, for appearing with us today. And I hope to come back for a much, much more extensive discussion of ants at some point, because I am particularly interested in ant intelligence and communication. I think that's pretty fascinating, because that tells you what the aliens might be doing.
Oh, I would love that. Yeah, this has been so much fun. Thanks so much for having me on.